Hello everyone and welcome back to your YouTube channel and welcome to this very short presentation. In this case, I have a short video regarding our paper presented in the IEEE Innovation Smart Grid Technologies Asia, also known as IEEE ISGT Asia 2022. This conference was between the 1st and the 5th of November at Singapore. And the title of this paper is Cyber Physical Co-Simulation Testbed for Real-Time Reactive Power Control in Smart Distribution Networks. And in this paper, we have several co-authors, and it's the collaboration between several universities. The co-authors are Raju Woggle, Giacchino Tricarico, myself, Pawan Sharma, Sharu Sharma, and Jose Luis Rueda. This is a collaboration. This paper is a collaboration between the University of Arctic in Norway, Polytechnico de Bari, TU Delft, University of Southeastern Norway, University of Exeter, and of course, all this work was developed inside the Digital Energy System Lab. And before we start, let me show you a brief agenda. I will start with a short introduction presenting the motivation behind this testbed. Then on section two, I will present the modeling of the cyber physical testbed. Then for the section number 3, I will present the implementation using the co-simulation framework between Typhoon HIL and the very famous software OpenDSS. Then on section number 4, I will present some simulations, real-time simulations and results. I will be supported by a video. And finally, section 5 is regarding the conclusions of this research paper. Well, let's start with the introduction. As you must be aware, there is a very strong pressure to reduce the CO2 emissions in order to overcome the climate emergency. And one of the most important sectors that we need to reduce the CO2 emission is the electricity sector. And as a consequence, we are having so much penetration of renewables, especially at distribution system. There are many countries inside continental Europe that the penetration of PV solar panels is extremely high. But this penetration of solar PV systems at distribution networks, they create several challenges. There are many challenges related, like, for instance, the voltage fluctuations that they are a consequence of the active power injection. So, as a consequence, the operation of the very old distribution system with the integration of those new technologies creates several challenges. Traditionally, we have been able to use offline simulation in order to fulfill some of the requirements, technical requirements of the distribution system. However, today, with the integration of those PV systems, the power electronic related to those PV systems, the interface to the grid, they produce new phenomena that require more detailed study. And that is the reason that we are changing the paradigm from the classical offline simulation to the real-time simulation. In this paper, we are really interested regarding the effectivity and efficiency of the reactive power control. As you must be aware, the modern PV systems, they have the possibility of using the inverter, the power electronic converter interface to the AC grid. They have the possibility of having communication, and with communication, we can control the reactive power production, and as a consequence, you can control the voltage profile and do many other services to the grid. For that reason, in this paper, we are developing and analyzing a cyber physical co-simulation testbed for real-time reactive power control in a smart distribution system. The co-simulation testbed is having basically two layers. One layer related with the physical components. In this case, we are using the framework of Typhoon HIL, specifically the Typhoon HIL 604 as a real-time simulator, and the cybernetic layer that is related with the informatic communication components. In this case, we are interested in co-simulation, and we are using the very well-known software OpenDSS. OpenDSS is a traditional software developed in US by EPRI that allows the calculation of the steady-state performance of the distribution network. It's oriented to distribution system. It has the possibility of modeling the network with full details and with a lot of flexibility, including radial topologies or mesh topologies, but also including single-phase or three-phase systems for balanced and unbalanced condition. For that reason, in this research paper, we select the use of OpenDSS as co-simulation network, co-simulation software with the use of the Typhoon HIL framework. But let me move forward and let me show you briefly some of the details of the cyber physical testbed. As I said before, there are two different layers, the cybernetic layer and the physical layer. The cybernetic layer is basically related with software. We have a graphical user interface that we are using to control the real-time simulation, but also to define, to control in a very sensible way what we know as the reference of the power converters. Also, we have in the cybernetic layer, we have also the OpenDSS, that is the distribution network simulation software that is used to obtain the RMS simulations, the steady-state behavior of the system. And with that, we are interchanging information with the host PC that is part of the physical layer that we are running the software, but at the same time we are running other software like Typhoon HIL Control Center that is used to interchange information and control the real-time simulation. As I said before, those two layers, they have different components and different elements. For instance, for modeling the test system, we are using the OpenDSS software, and we are using a very well-known test system. And this test system is basically modeled inside the OpenDSS as a simulation tool to calculate the load flow or the power flow of that network. But also we are installing some measurements and monitoring devices that they can obtain parameters and also take measurement for voltages, currents, and losses from the distribution system. On the real-time monitoring and control system, we are using the graphical user interface that is very powerful inside Typhoon HIL. We are using the graphical user interface that is developed inside the Typhoon HIL SCADA system that allows us also to use in real time the Python API to interchange information with the physical layer, in this case the real-time simulator. And now what I will present is basically the structure of the physical layer related of the model inside Typhoon HIL. Inside Typhoon HIL, we have a model for the PV system, specifically for the smart inverter. And in those smart inverters, we have the possibility of sending references of active and reactive power, and getting as a consequence from there the output of those PV systems. And here there is a very simple schematic for the implementation of the co-simulation framework. Step number 1, initializing the co-simulation framework between Typhoon HIL and OpenDSS. Step number 2, execute the real-time simulation with the help of the Typhoon HIL SCADA system. And step number 3, monitor and use the graphical display to show the output variables during the real-time simulation. Here, there is a graphical representation of the methodology. On the top of this slide, you can see the integration between and inside the cybernetic layer. You can see over here, we have OpenDSS, that is basically the engine that we are using for the RMS simulation for positive sequence model of the CIGRE medium voltage European testbed. On the other hand, we have here the software that is used to modeling, control, and run the real-time simulation inside Typhoon HIL. And in this case, the flow, the data flow and the simulation data between the two environments is use the Python API between those two communication flow, between those two software, two environments. And here at the bottom, you can see the physical layer. Inside the real-time simulator, we are including the model of the PV converter, the smart converter. We have the controller, but we are receiving the reference coming from the cybernetic layer. And here we have the data flow between the host computer and also the real-time simulator. More details about these implementations are shown here. And as you can see in the next slide, there are a more detailed implementation. The CIGRE medium voltage network is implemented here inside the OpenDSS. And here we have the API that is interchanging information with the reactive power control center and the HIL SCADA. What I'm telling you is that when we are running the real-time simulation, what we are doing is sending references from to the PV system, specifically to the smart inverter. We can modify here the references, and as a consequence, the ANT simulation that is inside the real-time simulator will send back the response of the behavior. And as a consequence, that data will be sent into the OpenDSS to close the loop for the co-simulation real-time implementation. Here at the next slide, let me show you the next slide. At the next slide, I have a more detailed graphical representation. They are very important components on the real-time simulation, in this case on the SCADA system from Typhoon HIL. We have the reactive power reference that is on the left-hand side. We have the active power reference on the right-hand side. We have in the middle a mimic, a graphical unit interface that is presenting results of the distribution network, in this case, the variables that we are monitoring. As you can see, we are presenting over here what is the active power and the reactive power and the total losses inside the distribution system, but also the RMS value for the voltages at the different measurement locations. There is a phasor representation here, but also a total active and reactive power presented here. Finally, there is an area here that is a panel. That panel is basically for the integration between OpenDSS and Typhoon HIL for the co-simulation environment, okay? Right now, what I will do is I will present a very important aspect, and inside the real-time simulator, we are running the real-time simulation and we are obtaining the voltages. And when there is a change on the references, you can see how the reactive power automatically will change to compensate the variation of those voltages. And that is basically the objective of this testbed. The testbed is designed in order that when the voltages are outside the limits, well, the reactive power that is produced by the smart inverter will compensate, producing more or less reactive power in order to go back the voltages inside the regulation limits. Well, now what I will do is I show a video. We are compiling right now inside the schematic software of the Typhoon HIL. We are compiling the model that we create, and right now the model is loaded inside the HIL. In this case, we are putting the model inside the Typhoon HIL 604. Right now, the model is imported, and right now we can run the real-time simulation. And now we are activating the co-simulation environment between OpenDSS and Typhoon HIL. Here you can see the references. My student is modifying the references, and you can see how the voltages are changing. However, what is important for you is that those voltages, they are changing as a consequence of variation of active and reactive power at the power inverter. If there is suddenly a cloud, you can see that the power production of the PV system can be reduced or can be increased depending on that. What is important is that if the voltages go beyond the limits, one activation signal will switch on the algorithm, the control algorithm, rescheduling the reactive power and sending a signal for the power converters in order to compensate the voltage variation. And that is the idea of this cyber-physical co-simulation testbed for real real-time reactive power control. Well, it's time for presenting some conclusions. In this paper, we present a co-simulation testbed for real-time reactive power control. We presented the methodology in the paper. You can read the paper and get the full details of that. In this case, we are using the Typhoon HIL real-time framework and the OpenDSS software for the co-simulation. And in this case, as we showed during the demonstration using the CIGRE medium voltage distribution network, we demonstrate that when the voltages go beyond the limits, the regulation limits, well, in this case, the testbed can be activated, can activate or generate a signal to activate the real-time active power control. Finally, there are here some references. There are some references over here. And you can also download the paper because it's already published in the IEEE Explorer. It's almost time to close this presentation, and I would like to say again thank you to all the institutions involved here, the University of the Arctic in Norway, Polytechnico de Paris, TU Delft, University of Southeastern Norway, and University of Exeter. And I would like to tell you that DHENSYS Lab is an initiative for research and innovation, and is open to the participation of any people that are interested on the area of digital energy system, real-time simulation, and hardware in the loop. For that reason, if you are interested on DHENSYS Lab, please drop an email, contact me, and I will be extremely happy to hear your idea and to try to establish future collaborations. Thank you very much for watching this video, and I will see you at the next one. Bye now.